All right, Dalton's law of partial pressures next on the docket here. So Dalton's law of partial pressures is fairly simplistic, at least in its underpinnings. So if we had a container here, and in this container, it contained nitrogen gas, oxygen gas, and carbon dioxide, let's say. Then the total pressure inside this vessel here would equal the partial pressure of nitrogen plus the partial pressure of oxygen plus the partial pressure of carbon dioxide. So we call these partial pressures. And they call them partial pressures. It's just because the partial pressure of N2 is just the part of the total pressure that N2 is responsible for. And the more moles of a particular gas, the greater the part of the pressure it's responsible for. So let's put this a little more concretely here. Let's say I tell you here that the total pressure inside this vessel is 50 atmospheres. That's your total pressure. So, and then I tell you that there are 14 moles of N2, 5 moles of O2, and 1 mole of CO2. So, and the question then is, what is the partial pressure of each one of these three gases? So here's the idea. What percentage of the gases in here are nitrogen? What percentage? How do you get a percent out of this? So what percentage of the moles of gas are nitrogen? Yeah, part over whole times 100, right? And so the part would be 14. What would be the whole? 20 total. And 14 out of 20 times 100 is what percent? Well, 14 out of 20 is the same as how much out of 10? 7 out of 10, and that's 70%. Well, if 70% of the moles are nitrogen, then 70% of the pressure is his partial pressure. If he's responsible for 70% of the moles, then he's responsible for 70% of the pressure. The way that comes out in an equation is the partial pressure of nitrogen is equal to the mole fraction of nitrogen times the total pressure. Now don't be scared by this. This is not an X, it's the Greek letter chi, and it stands for mole fraction. Don't be scared by a mole fraction. The mole fraction is the same thing as a percentage, except you're not multiplying by 100. So notice, instead of taking 14 out of 20 times 100, we're just going to take 14 out of 20. It's the fraction of the moles that are nitrogen. And so in this case, calculate that out. We got 14 out of 20 times the total pressure of 50 atmospheres. So, and what does this come out to? And it comes out to 35 ATMs. 35 ATMs. And that is 70% of the 50 atmospheres. Okay, so we can do the same thing for O2 and CO2. Partial pressure of O2, what is, well, what fraction of the moles are O2? 5 out of 20, and you can reduce that down if you want to. I kind of like mindlessly just putting 5 out of 20 times the total pressure of 50 atmospheres, and that gets me, well, again, 5 out of 20 is 1/4. What's 1/4 of 50? .5 atmospheres. Question?
Why are you using 20?
So, because we have 20 total moles. So, and again, it's just the part over the whole to get a mole fraction. So again, same thing like the percentage, part over whole, except we're just not going to multiply by 100. Only difference between a mole fraction and a percent. Welcome. Cool. Now we can do this same calculation for CO2, but you probably already know the value for CO2 without doing it. What is the partial pressure of CO2? Well, there's only 1 mole, but what's the partial pressure? And why am I not going to run, why don't I have to run through this calculation to get there? Yeah, it's just, they all add up to 50 total, so what's left, right? So it's 35 plus 12.5, that's 47.5, so what's the remainder? 2.5 more to get to 50. And so here, by Dalton's law of partial pressures, the remainder is 2.5 atmospheres. Now, again, I could have gone through this process and said, yeah, it's 1 out of 20 for the mole fraction times the total pressure of 50 atmospheres. And I could still do that, but I didn't have to in this case because they all had to add up to a total of 50. Cool. That's all Dalton's law of partial pressures says.
So what kind of questions would they ask us?
Exactly the ones we just answered. They might tell you all this information and ask you for any one of these three. Could be any of the three. Cool. Let's talk about density of a gas. What is the definition of density in a general sense? Yeah. Density is mass per volume. Great. So we can take this here, and they may give you the mass of a sample of a gas and its total volume, and that allows you to calculate density. But we usually make it just a little bit harder than that. So for a gas and for a gas only, you can actually derive a slightly different, or a fairly different expression to calculate the density. But again, only for a gas. And we're going to derive it from the ideal gas law. So if you look, PV equals nRT. The closest you can get to getting something looking like mass over volume is to rearrange this and get something that looks like moles over volume. And you get P over RT equals N over V. But it's not the same thing as density, right? Moles over volume, technically if that's moles over liters, that's kind of like molarity. So, but we're not quite there in this case. So if you look here though, do you know how to turn moles into grams? If I told you I had 2 moles of, helium gas. Helium weighs 4. If I had 2 moles of helium gas, how many grams would that be? 8 grams, right? It's 4 grams per mole. I got 2 moles, that's 8 grams. So how did we get there? We multiplied by what? The molar mass. And so that's what I'm going to do. I'm going to take this and multiply by the molar mass. But if I multiply that by the molar mass, are these still equal? No, but in algebra we learned anything you do to one side, do it to the other side also. And now moles times molar mass is the same thing as the mass. And so now I find that this is another way of expressing the density of a gas. And so we can say it's equal to pressure times the molar mass over RT. Cool. We won't always give you this expression. You may see this showing up on the front page of your exam, you may not. So you can derive it by all means. So a couple different ways to go about it, but it is something you should be proficient in using. So, and it can be given in one of a couple of different ways. There's a variety of variables in here. I can give you the mass of a sample of a gas, the volume of a sample of gas, the pressure and the temperature, and then say what's the molar mass, or say what gas is it. So, and if I said what gas is it, your goal is still to solve for the molar mass, and then look at the choices and see which gas actually has the molar mass that you actually solve for. So, but again, there's a number of variables in here. I got to give you all of them except one and have you solve for one. But again, involves density of a gas. I want to bring up another important principle, STP. STP, what does that stand for? Standard temperature pressure. So what is the standard temperature and pressure? 0 what? 0 Celsius. And 0 degrees Celsius is the same as? Good. So, and then what's the standard pressure? Good. Pressure equals 1 atmosphere. Now, next semester, we'll define what we call standard conditions. So, in kind of a different context in thermodynamics. And standard conditions are a little bit different. Standard conditions uses the same pressure, but standard conditions technically doesn't really assign a temperature. So, but if we do associate a temperature with standard conditions, it's usually not this one. We usually assign for standard conditions room temperature if we're going to associate a temperature with it all, which is usually 25 degrees Celsius or 298 Kelvin. But this is not standard conditions. This is distinct from it. This is STP, standard temperature and pressure, and we got to remember it's 0 degrees Celsius. So next semester, just remember there's a difference between STP and standard conditions. But for now, we're only going to deal with STP, and it is indeed the freezing temperature of water. So when you're at STP, so many gases have fairly ideal behavior, because this is considered a rather high temperature. And 1 atmosphere is considered a rather low pressure. And those, again, are when those two assumptions we made are satisfied best. Cool. The other thing we got to remember about this is if you take these conditions, and you take and plug in 1 atmosphere for the pressure, 273 Kelvin for the temperature, and plug in 1 mole of gas. And notice it doesn't matter what gas, 1 mole of any gas. Take your pick. And then you solve for V. What does V come out to under those cases for 1 mole of any gas? Well, it comes out the same, but there's also a specific number that you probably will recognize as soon as I write it. At STP, the volume of 1 mole of any gas is 22.4 liters. This is probably worth memorizing. It's a pretty standard number. It shows up pretty commonly, but it's probably worth memorizing because we do so many problems at STP. And we do them at STP because we've given you this number. So it kind of works hand in hand. So for example, so let's say we're dealing with the decomposition of calcium carbonate. Decomposition of calcium carbonate. And I say that I start with 200 grams of calcium carbonate. And the questions I could ask you, well, how many moles of calcium oxide does that produce? Or how many grams of calcium oxide does that produce? Regular stoichiometry you've done. I could do the same thing over here. I could say how many grams or how many moles of carbon dioxide does that produce? Same thing you've done with stoichiometry. But with this chapter, we can now take this one step further. I could ask you what volume of carbon dioxide is produced. And I could say under any set of conditions. But the most common set of conditions we're going to ask you for is at STP. And so that is my question. Assuming this reacts completely, what volume of carbon dioxide at STP is produced? What's that? So we're going to do this in our head first. And again, the only reason we're going to do this in our head is because I picked nice numbers. So if you look, 200 grams of calcium carbonate, you'll see this works out really nice. Calcium weighs 40, carbon weighs 12. 3 oxygens that weigh 16 each is 48. 48 plus 12 is 60. 60 plus 40 is 100. If 1 mole of calcium carbonate weighs 100 grams, then how many moles do we have? 2 moles. And if I have 2 moles of calcium carbonate that reacts completely, how many moles of carbon dioxide could that produce? 2 moles. A 1-to-1 ratio is the same as a 2-to-2 ratio. And if I have 2 moles of any gas, including this one, at STP, well, if 1 mole of gas is 22.4 liters at STP, then 2 moles of gas would be 44.8 liters. And that's how I asked that. Now, what if I didn't say STP? What if I said, what volume of carbon dioxide at such and such a pressure and such a temperature? Well, unfortunately, then you need to find the 2 moles again, and then plug that in for N in PV equals nRT at that point. But if it's at STP, we got to cheat. So the way this calculation overall would end up looking is that we'll convert to moles first. And again, 1 mole of calcium carbonate weighs 100 grams. And then I can convert that to moles of whatever the gas is, in this case CO2. And it's a 1-to-1 ratio. 1 mole of CO2 is produced from 1 mole of calcium carbonate. And we go there. And again, if I didn't have STP, I would stop the calculation here, solve for N, and plug that in for for N in PV equals nRT. But in this case, I can take it a step further. I can say that 1 mole of any gas, including CO2 gas, at STP takes up 22.4 liters. And multiply that all the way through, and lo and behold, we get what we just did in our head. So, and then our volume would equal 44.8 liters of carbon dioxide at STP. So technically, you don't really have to memorize that 22.4 number. However, it would have saved you a little bit of time not having to plug this all back into PV equals nRT in this case. And again, giving you conditions of STP is pretty common on this exam.